So our problem that we're still thinking about is that of coloring a map. And what we saw last time is that given a map of regions, we can, instead of thinking of this map, we can take the dual graph that turns every face, for example, New Mexico, into a vertex. And then we'll connect two vertices, so the one corresponding to New Mexico and the one corresponding to Arizona, because New Mexico and Arizona share a border. So that will give us an edge between these two vertices. So our problem of coloring a map, for example, of the Western United States, becomes the problem of coloring this planar graph that we get by taking the dual. So remember, the dual of a map is a planar graph. So the question we're really trying to answer is, what's the chromatic number, the minimum of colors needed to properly color a planar graph? Now, K4 we saw before is planar. So here's an example of realizing K4 is a planar graph. And of course, we need 4 colors for this because every pair of vertices is connected. So the chromatic number of K4 is 4. So we expect that a planar graph will need at least 4 colors in general. Of course, there are examples that can use fewer, but this example we saw because of Nevada, we need exactly 4. And the question is, do we need more than 4? Might it be that we need, 12 colors to color a graph? And that's what we're going to explore next. So the theorem that we're going to prove this time is the 6-color theorem. So the theorem is that any planar graph is 6 colorable. So if you're a cartographer, then you know that the most number of colors you need in your palette is 6. How do we prove such a thing? Well, it's nice to work by induction. That's one of the easiest strategies for proofs that we've seen. And for graphs, when we're doing induction, often it's on the number of edges or the number of vertices or the number of faces. If you have a planar graph, you can talk about those. For us, it turns out that the number of vertices is what we're going to want to use. So let's do the proof by induction on n equal the number of vertices of our graph G. So we'll need a base case. And what's the base case? Well, we can say n equal 1. And really, the base case can be n. So really, it can be any n less than or equal to 6. Because if you have at most 6 vertices, then you could color them all different colors if you have 6 colors. So this is definitely 6 colorable, right? So any graph with at most 6 vertices, we can just use a different color for every vertex. It's definitely properly colored in that way. So we're good to go. What is our inductive hypothesis? So the inductive hypothesis, any planar graph with strictly less than n vertices is 6 colorable. That's our inductive hypothesis. So the idea is that when we have a planar graph, if we take away a vertex, for example, if we took away California, right, then it's still a planar graph. So it's not going to be worse. And then the idea is that when we add California back, we want to show that, okay, we added California back, but we didn't need more colors when we did it. But if you notice in this very specific example, the problem is that when we add California, we absolutely do need another color. The way that I've colored this graph, if I take California away, the graph is 3 colorable. But with California, it's 4 colorable and not 3 colorable. So we need to be careful in how we do that. And it turns out we're gonna pause for just a second, and we're going to prove a lemma. So lemmas are these little statements that help us prove theorems. And the lemma is that when we have a planar graph, there's always at least one vertex that doesn't have lots of neighbors, okay? And that's what's going to allow us to do the induction. So let's do a lemma. And let's see, how do we want to state this? Every planar graph, those are the ones we care about for this example. Every planar graph has a vertex, at least one, but maybe more than one, of degree less than or equal to 5. Let's go ahead and pause with that lemma. Let's take the statement for granted for now, and let's see how that helps us continue to prove our theorem. So we're going to use the lemma, and we're going to say, okay, so let V be a vertex such that the degree of V is less than or equal to 5. The lemma says that such a vertex exists. Okay, now what we're going to do is, by the inductive hypothesis, if we take G and we remove the vertex V, this is 6 colorable. It has 1 fewer vertex, so it's going to be colorable with 6 colors. So go ahead and 6 color V. And now think about this is V. Okay, V has these 5 neighbors, 1, 2, 3, 4, 5. Among them, we use 5 different colors, maybe fewer. It's possible they don't all need different colors. It could be this one was also purple, not green, but that's fine. At most 5 different colors, but we have 6 colors to work with. So we can just now go back and color V. So since V has less than or equal to 5 neighbors, there are at most 5 colors used among them. So color V with any other color among the 6 choices, the 6 color options. And that's it. Now we're done. So now we know that, okay, if we had something that was 6 colorable, so what we're going to do is we're going to take V out, right? Color the graph with 6 colors. And now when we add V back in, we know that because V only has 5 neighbors, there's some color we haven't used yet among the neighbors, and that's the color we can use for V, and then it's going to be a properly colored graph. So this is a really great lemma. It definitely helps us prove the theorem. But now we need to prove the lemma. Okay, we've reduced the problem. How are we going to prove the lemma? Well, notice that in our theorem, we actually didn't use the fact that G was planar anywhere, except in this lemma. This lemma relies on the graph being planar. So what do we know about planar graphs that might help us prove this lemma? Well, we know from Euler's theorem that the number of vertices minus the number of edges plus the number of faces is equal to 2. Okay, now I'm going to throw in a claim. This claim I'm not going to prove because I'm going to leave it to you to prove for the homework. For a planar graph, we can talk about faces, and I claim that 3 times the number of faces is less than or equal to 2 times the number of edges. So think about that for your homework. That's going to be something that you can just prove by thinking about the structure of faces and edges. Now let's combine Euler's theorem with this observation. So in order to use it properly, let me go ahead and multiply Euler's equation by 3. So we have that 3v minus 3e plus 3f is equal to 6. Okay, 3f, well, that's where the claim is going to come in. So let's go ahead and maybe move that one over. So that's going to tell us that, let's see, we'll move it to that side. So we're going to get 6 minus 3v minus 3e equals, I think I messed that one up, there equals 3f, which is less than or equal to 2e. Now what do I want to do? Now I want to take this part and solve for e, okay? So I'm going to get e on the one side. So I'm going to get, let's see, 3e minus 2e, that's just going to be e on the left, is less than or equal to 3v minus 6. Okay, now how does that help me? Well, remember what I'm trying to prove something about is the degree of a vertex. So if I take the sum for all vertices I in my graph of the degree of vertex I, what is that? Well, if you just think about the edges, every edge will be counted twice because it has 2 vertices on it. So this is going to be twice the number of edges. So now if we use this equation that we finally got, we know this is going to be less than or equal to 6v minus 12. And now we're getting somewhere. So what does that tell us? What does that tell us? It tells us that v, remember that's the number of vertices. So the average number of vertices, that's 1 over v, the sum, I and v, sorry, it's the average degree. This is equal to the average degree of a vertex. This is less than or equal to, divide the other side, 6 minus 12 over v, which, okay, whatever that is, it's less than 6. So if the average degree is strictly less than 6, that means there has to be at least one vertex that has degree less than 6. And that concludes the proof. So that's the proof of the lemma. We can see that in a planar graph, the average degree of a vertex is going to be 6 minus 12 divided by v. Well, less than or equal to that. And that's something less than 6. So we're going to have at least one vertex of smaller degree. And we can see that here in this graph, actually most of the vertices have degree less than or equal to 5. This one has degree 6. So it's not true that every vertex has degree less than 5, but the average degree is less than or equal to 5. And so that allows us to prove every planar graph is 6 colorable. The question is, can we do better? We know we need at least 4 colors and at most 6 colors. So do we need 4, 5, or 6?